Hello and welcome back to Lesson 3. So far, we've seen that a range of analytical solutions exist for some of the simpler generalised Newtonian models, and that these solutions enable us to quickly estimate pressure drops through certain geometries. They also allow us shear rates and shear stresses to be calculated, and with the correct numerical code, deformation. Typically, the parameters in these equations are influenced by the presence of elasticity, hence data obtained from generalised Newtonian models must be treated with caution when dealing with flows of polymeric materials. In this part of the lesson, we're going to see how to set up and solve Cauchy's momentum equation for the flow of a power law fluid in a tube. Whilst we've seen the end result before, the motivation now is to understand how to obtain the correct parts of the equation of motion to solve. Sometimes it may be necessary to obtain a numerical solution rather than an analytical one, but this still requires the equation of motion to be written correctly for the problem of interest. So, let's start by listing some assumptions that we have to make in order to approach the problem. Here on the board, I've first of all drawn a diagram. That's always my step one when I'm solving a flow problem. Understand the flow, get a mental model. So my diagram here is simply that of the cross-section of a pipe. The pipe has a radius of R1, it has a length L, and the pressure varies across that length L from P1 at the start to P0 at the end. Now, let's make some assumptions. We have to make assumptions when solving any model. So first of all, I'm going to assume that my flow is steady. Steady in terms of time variation. So any change in velocity is zero. I'm going to neglect gravity because my pipe is horizontal and the effect of gravity is therefore going to be negligible. I'm also going to assume that my flow is slow. It's going to be of a low Reynolds number if we look at the value of eta for my viscosity. So it's definitely laminar. Moreover, rather than just being laminar, it's going to be essentially non-inertial. And if we remember how we solved the Navier-Stokes equations for essentially non-inertial flow, that means we can usually set the rho big dV by big dt term equal to 0, which is a really good simplification. And it's true in this case, because if it's steady, there's no time-based acceleration. If it's non-inertial, it's creeping flow, and that's great. But also we can see there's no divergence or convergence of flow here. There's no spatial acceleration. So that total derivative is going to be 0. Let's think about the velocity. My flow velocity is along the pipe, which is my z direction. So it's the axial direction. So the only velocity I'm assuming I've got is that z direction, that axial direction velocity. There's no radial velocity, there's no tangential velocity. And thinking about that axial velocity, it only changes with radius. There's a maximum flow velocity in the centre of the pipe, and there's going to be the no-slip boundary condition on the walls, where the fluid is moving with the velocity of the wall, which in this case is stationary. Okay, let's think about the pressure. The pressure is only changing in the z direction. For those of you who remember 640, we'll say that pressure can change across curvature of streamlines. These streamlines are straight and parallel. There is no streamline curvature. There is no pressure change across those streamlines. Pressure changes in the direction of flow. It's going from P1 to P0 over my length L. So now what I'm going to do is draw another little diagram to visualize the stresses in this particular flow field. So there are my coordinate axes, my radial and my axial coordinate, r and z respectively. There's a little elemental cylinder, a little bit of cylinder for my pipe flow. And what I'm going to say is, look, at one end I've got P1, at the other end I've got P0. Those are my pressures. Those pressures are not equal, therefore they have to be balanced by other stresses. And those stresses are acting on the radial face in the z direction, tau rz. Remember that subscript order. The first subscript is the face first, if you want a way of remembering it. And the second subscript is the direction. So tau rz is a radial stress in the z direction. So that's going to be my force balance. We've already said we've got a cylindrical geometry, but the thing to tease out of that is the centerline symmetry. And that is why I've placed my axes on that symmetry line, because when r equals 0, I've got a turning point. It's my point of maximum flow velocity, and that makes the calculation or the algebra very much easier. Let's think about this from the nature of boundary conditions now. We've got a pressure-driven flow. There is no shear stress on that centre line. There's no shear stress because that's our point of maximum velocity, which is a turning point. Therefore, a turning point has a derivative of 0. And if we think about the relationship between shear stress and velocity, shear stress relates to shear rate, and the shear rate is equal to a velocity gradient, and my velocity gradient is 0, so therefore there's no stress at that centre line. We've already mentioned we've got no slip on the stationary walls, so writing it algebraically, that means my axial velocity, Vz, is going to be 0 at the point where my radial coordinate little r is equal to the inner radius of the tube capital R. Okay, so there's my list of assumptions. So what we're now going to do is to write down Cauchy's momentum equation and simplify it. This is very similar to the workflow that we used for Navier-Stokes. So there's Cauchy's momentum equation. Now don't forget, if that looks a bit scary, Cauchy's momentum equation is just simply a statement of force equals mass times acceleration. Forces on the right-hand side in blue and in purple. Mass, well, density is mass per unit volume. Acceleration, that's all wrapped up in that big d by dt of v term. Don't forget that that is equal to a spatial acceleration, partial dv by partial dt, plus a temporal acceleration, partial dv by partial dt, plus a spatial acceleration, v dot grad v. We have no acceleration either spatially or temporally in this problem, so therefore the left-hand side of this equation is 0. We've neglected the force of gravity, which I put in blue there, because we've got a horizontal pipe, we've got a very high viscosity fluid. It's not going to have any significant impact whatsoever. And so all we're left with, in terms of Cauchy's momentum equation, is a pressure gradient and its relationship with the divergence of the stress tensor. Which sounds a bit of a mouthful, but don't forget that we can simplify this down very, very easily because we've only got flow in one direction. So let's have a quick think. If we look in Baird and Collias, table 2.7, we find expansions of Cauchy's momentum equation for various coordinate systems. And if we think of a cylindrical polar coordinate system, such as that we use to describe a pipe, then we'll see that if we've only got pressure varying in the z direction, and if we've only got radial stress acting in the z direction varying with radius, then that vector form of the pressure gradient equaling the divergence of the stress tensor actually is a far simpler statement. It's just simply partial dp by partial dz is going to be 1 over r partial d by partial dr of r times tau rz. Those are the only terms in that Cauchy momentum equation that are non-zero. And this is the crucial step really, and the crux of this lesson in many ways, is getting to that point. Figure out how to simplify down that equation to a set of terms that we can then solve. And so with a little bit of integration, we can get an explicit statement of what stress is. Tau rz is partial dp by partial dz r upon 2. One integration step. The first integration constant was 0. Otherwise, we have a term knocking around with the natural logarithm of 0, which is infinity, which we know just isn't the case. Okay, so that's step number 1. But we haven't actually included any rheology yet, have we? Neither have we actually got to a velocity field. We've simply got a relationship between stress and pressure gradient. So let's now take the next step. That involves stating our constitutive equation. So there's our constitutive equation there on the whiteboard. My stress tensor tau is equal to my viscosity, or my apparent viscosity, eta, times my stress shear rate tensor gamma dot. And we know that for a power law fluid, eta is my consistency index capital K, multiplied by the magnitude of my shear rate tensor gamma dot, raised to the power of n minus 1, where n is the power law index. Okay, fine. Let's examine the form of my shear rate tensor gamma dot. The important thing to always do when solving these problems is to simplify things as soon as you can. So for simple pressure-driven flow in a pipe, gamma dot just looks like that. Remember that these tensors are always symmetric. They have to be, and if you've forgotten the reasons why they're symmetric, refer back to the course 640. And the only entries in this strain rate tensor are partial dvz by partial r. So what we need for the power law model is a statement of the magnitude of this strain rate tensor. And remember, the magnitude of a tensorial quantity is the square root of half of the double dot product of that tensorial quantity with itself. And if we work that through for this particular example, it is the square root of 1/2 times 2, so 1, times dvz by dr squared. So simply, we could have seen that very obviously to start with, that the magnitude of the strain rate is simply partial dvz by partial dr, but I've derived it formally there in case of those we're dealing with a circumstance where the strain rate tensor is more complex. So tau rz is equal to dp by dz r upon 2, which in turn is equal to k times dvz by dr raised to the power n. And that gives us something else to integrate. Okay, so let's do it. We can integrate with a boundary condition that vz is going to be equal when r equals r. That's my no-slip boundary condition. And that's the only equation we need to solve for our velocity field. So if we'd got this far to a point where we couldn't analytically integrate this equation, that's what we'd solve numerically. So let's solve this analytically. And what we do when we do that is we achieve this answer here. And I encourage you to work through that and get to this end result. Okay, good. Now, in the previous lesson, we saw how to set up the lubrication approximation. We needed a volumetric flow expression for a fluid, and we gave an example of that for Newtonian. We can do exactly the same now with power law. We've just taken the first step to get our velocity field, so let's carry on. Let's change our geometry subtly. We're still in cylindrical polar coordinates. We've still got a pressure drop going from P1 to P0 over a length L. We're still starting our geometry with a radius R1, but now it tapers slightly to a smaller radius R0 at length L. If you recall from the previous lesson, we said, look, this is just a simple linear variation of radius with respect to length that has that equation there. R of z is R1 minus z upon L, R1 minus R0. Also, now let's rewrite our pressure gradient in terms of pressure drop. And remember that a negative pressure gradient, one that decreases as we move along the flow, is what we term a positive pressure drop. Because if our pressure gradient was positive, our pressure would increase along the axial direction, and we wouldn't end up with flow in the sense that we've marked on the board there. Okay, so if we think about volumetric flow rate, that's a starting point for the lubrication approximation now. It's simply an integral of our velocity field over our area. I'm not going to repeat those steps now. I would encourage you in your own time to make sure that you do understand where that equation has come from and that you can derive it from the velocity field. Now, I've highlighted the radial terms there and the power law index terms there in sort of pink and orange respectively, and I'm just going to manipulate them a little bit, rearrange them, put them in different places, just to make the rest of the algebra a bit easier. I'm going to separate the radial terms to start with like so. Then I'm just going to rearrange the equation like so. And that just allows me to substitute in the expression for the shape variation a little more easily and just get a slightly neater expression. Okay, if I do substitute the radial shape variation into that expression, I'm going to have big R of z equals R1 minus z over L, R1 minus R0. I'm going to put a parameter substitution here to make the integration a bit easier. Remember, when you do that, of course, you need to change your du's and your dz's. You need to make sure that they're compatible. And you just need to address your boundary conditions and be careful, and that little u is R1 when z equals 0, little u equals R0 when z equals L. Okay, I've called a substituted parameter here u. I could have quite happily just kept it as R. So I'm going to integrate that expression. And when I do, I end up with an expression for the pressure difference between P1 and P0 as a function of power law parameters, consistency index and power law index, the volumetric flow rate Q, and the shape variation R0 and R1. So there we have the lubrication approximation for flow in a cylindrical taper, and it followed exactly the same workflow as we used for Newtonian lubrication approximation for flow in a cylindrical taper, but now we've just got the power law version. So let's summarize a few key points. We started really by motivating ourselves, saying, look, we're going to be looking at some flow problems. We might want to solve these flow problems. We might not always be able to solve them analytically, but if we're solving them numerically, we still have to set up the equations of motion correctly. And we started this part of this lesson by doing exactly that. We took Cauchy's momentum equation, we drew a diagram, we made a load of assumptions, we had a mental model of which way the stresses were acting, which way the flow's going, and then we were able to simplify Cauchy's momentum equation down to a very simple differential equation that in this case we could actually analytically solve. And the solution to that analysis was one you'd seen before. It's one I encouraged you in the last part of this lesson to go and have a look at. But we've just derived it using a slightly different methodology here, because the methodology that we've used here we can now apply more widely to more complex constitutive equations where we do have to solve numerically, and we'll see that in later parts of this lesson. So the final thing here is that we extended the analysis to say, hey look, last lesson you looked at the lubrication approximation for Newtonian fluid. You started effectively from a velocity profile and a volumetric flow rate, equation of change for shape, and then matched the two together and integrated. It's exactly the same here. We got the expression for our velocity profile. From that we extracted a volumetric flow rate, which involves a differential equation pressure drop. We plugged into that the change of shape as a function of length, and hey presto, out we achieved the pressure drop as a function of length for a tapering geometry for a power law fluid.